Okay, seems like almost 30 minutes the recording didn't go well, but I hope now it's okay. So let me repeat what I said here. The question is, so if so the claim is kernel of D is the harmonic form of even when D is equal to D plus delta, and the co-kernel is of D is harmonic form of the odd. Yeah, maybe I should use D plus number. Okay, so this is the claim. And since as a vector space, they are isomorphic to dynamical homology or even as a vector space. As a vector space. So maybe I should use this drum harmonic drum harmonic. Yeah. So so the question is, so D plus lambda omega equal to 0 means the D omega equal to 0 and lambda omega equal to 0. And this is the same as the harmonic like harmonic operator, which is equal to D lambda D omega equal to 0. So therefore, this means the omega is inside harmonic form. And then you can always take the element of dynamical homology of an R. So the representative of the omega as a harmonic form. And of course you can add the exact form, D lambda, you can add D lambda, but in that case, nabla of D, in this case nabla of omega is indeed equal to nabla D lambda, which is not equal to, which is not inside which is not equal to D. That's Hodgson measure. If lambda is not trivial. Is not equal to 0. So that's if not. So that's what it means. So now for the kernel of D can be understood as the harmonic, even harmonic form, or kernel of D can be understood as odd harmonic form. And as a vector space, they are isomorphic to dynamical homology. So the index will give you another thing that's to give you a reference. Okay. Okay, now recording is okay now. It's not charging? What happened? Okay, hopefully it's okay. Sorry, my laptop is not working very well. Okay, let me move on, but so let's move on to complex word. So complex word, you can have the holomorphic differential operator. So another holomorphic differential operator. So it's complex manifold, and this is holomorphic. Vector bundle. Holomorphic means complex. So complex manifold is just you have the same. I mean, you have the manifold M, but you have a trivialization, not trivialization, local open patch to indeed C to the N, C to the N to phi alpha, phi beta, and from here to here phi alpha inverse phi beta. So this is holomorphic function. It becomes holomorphic function. So U alpha and the U beta. Okay. That's holomorphic function. And then, so homomorphic vector bundle is that you just consider here, and you have transition function. So the vector, and you have a vector C to the R, and then transition function is indeed pi inverse alpha U alpha beta to pi inverse beta of U alpha beta means U alpha. No, of course I just consider that between them is U alpha beta. Here's U alpha beta. U alpha beta to the times C to the R, U alpha beta times C to the R, and the Q B is mapped to Q sum G alpha beta Q in the B. Okay, and this is inside a holomorphic function. So it's the holomorphic function. Holomorphic valued in. I mean, if it is vector bundle, I mean, for instance, UR. Valued in UR. It's everything becomes holomorphic. So or complex word. It's just complex function. It satisfies Cauchy-Riemann equation. It means the holomorphic function, and this is a holomorphic function. That's it. And then So you can define, and if you consider the differential form in complex manifold, essentially zero whatever p of M can be understood as section or just spanned by some manifold of DC one bar, which DC P bar. Okay. So here you have a homomorphic, it's Cn, so the function, the coordinate is Z1 to Zn and W1 to Wn. And each local patch, you can define the dZ1 bar, dZ1, dZ2 bar, and so on. And you can span by times some function. Some function over whatever function over, it can be dependent on Z2 bar. And then the homomorphic form, this is anti-homomorphic form, and this is a homomorphic form. dZ1, which okay, yeah. As far as does it only depend Z bar? To be honest, I already forgot. I should have known that. Sorry, I may be wrong here. Maybe it only depends on Z bar. I already forgot. How do I know that? I think it only depends on Z bar. My guess is only depends on Z bar. Yeah. It should be Z bar, and this only depends on Z. Sorry. Yeah. So this is anti-homomorphic P form. P form, and this is a homomorphic P form. Maybe I can. Yeah. So, and then when we consider the section, so you can define the double operator, so it's called double operator, which just map the section of complex homomorphic vector bundle to the tensor with the anti-homomorphic vector differential form in such a way that so that some dZ bar yeah, I think I should I1, IP, I1, which, okay. So then, again, so this double operator, it's called double operator. It's called double. Is equal to 0. So that one can consider so-called double complex. And this is a bit difficult subject. And you have to really work out by myself, but so this is called double complex. It's complex version of drum complex. Phi is a section of the E and also section of. So she wants back the. Sorry, do you want the charger back? Yes. Okay. Okay. Nobody has the MacBook charger, right? Do you? Do you have MacBook charger? Thank you very much.
Okay. Try Type-C charger.
Huh?
Maybe it can use it's a Type-C charger. And it's not for MacBook original.
Oh, that would be nice. Thank you very much.
I'm not sure
it should work. Oh, thank you very much. Yeah. Yeah, wonderful. It's working. Thank you. Yeah, it's working. Huh? Oh yeah, it's working. Thank you very much. So the phi is the element of a section of E times the some anti-homologic derivative. Okay, and then the cohomology of this one is indeed can be written as follows: is again the kernel. Kernel of double operator, image of double operator. So that's called double cohomology. Homology, and then M can have the again the Hermitian metric. So that it can be understood as some kind of Riemannian manifold, and you can define it the same way, the dual of the double operator by using Hodge-Taub. So this will map gamma E. I mean, it's a bit, too schematic. Omega P minus 1, 0, M. And then you can do the same exercise. It's the drum case. Okay. You can do the same exercise, and then the Hilbert-Riemann log is indeed mentioned that this is equal to sum of dimension H0P and P, where P is even, minus sum is odd dimension of H0 P and E. This is the analytic index, and then this is indeed can be written as the churn of E and top of N. So this is called Hilbert-Riemann log. So this is called Hilbert-Riemann log. And remember, so again, so here taught class appear, the one I defined in the beginning of lecture, it appear in the character classes, but you have to take a wedge product of churn class of E. Sorry, it's not churn class, churn character. Okay? It's churn character of E. So this is churn character of E. Again, so you have analytic index is associated by some topological quantity. So this is very important theorem for complex manifold, and in particular, so this will show up indeed. This will show up indeed called so-called Chern-Simons. So this theorem will show up in the states in Chern-Simons theory. So this is the some people might have. I mean, I will explain a little bit about Chern-Simons in the next lecture, but it's states in Chern-Simons. Chern-Simons is indeed a trace of A dA plus 2/3 of A wedge A. So this is the actions in Chern-Simons. So M has to be which dimension? It should be 3 dimension. It's a 3 form. A is 1 form, so it's a 3 dimension. So this is called Chern-Simons action. And then I'm not gonna explain in detail, but just flavor. I don't know. I mean, so this is look like completely different from. I mean, it's really look like a purely mathematics, but I just give you some connection to physics. This is 3-dimensional manifold. This is called Chern-Simons action. And then, I mean, usual Hamiltonian quantization formalism M3, you have a bulk and a boundary. You can associate, if you have a Chern-Simons theory, you can associate some Hilbert space at the boundary. And this Hilbert space at the boundary can be understood as the homomorphic section of the okay, it's a bit difficult. Modular space of Lac connection of sigma of complex G and LK, L to the K. So it's a bit difficult. I will explain what's the modular space of Lac connection of a Riemann surface. L is some line bundle, and the K is the Chern-Simons level. And it's the state is isomorphic. It's a finite dimensional object. It's isomorphic to holomorphic section of the bundle of a so-called modular space of Lac connection. And indeed, this dimension can be computed by using Hilsberg-Brunel. I mean, this is a bit difficult subject, but to consider some quantum Chern-Simons theory, you have to use Hilsberg-Brunel. Anyway, this is exactly the place I'm working on. This is famous work by Whitman. This is the famous paper by Whitman. QFT and John's polynomial. I mean, it looks like it's purely mathematics, but you need it for quantum Chern-Simons theory. Maybe I can just use this blackboard. Okay, so let me move on. Okay, now I'm going to talk about Dirac operator. The Atiyah single. This is really Atiyah single. Index Dirac operator. I mean, this is also it's a bit deep subject. I can spend like a few more lectures about the Dirac operator, to introduce Dirac operator mathematically and so on. It's a bit. So I did the. I by using my I mean this one. I use this one. I introduced spinor group, right? Spinor group. By it's a double couple. And then so spin group of n dimension is double couple of SO n. It has a so-called Skinner representation. From here, one can just define the so-called Dirac operator. Now, fortunately, I don't think I can explain more in detail in the Skinner representation. This is really also really the place math and physics intersect. That's why Atiyah and the Atiyah single index theorem is used by even physicists. But I just use the example of R4. In R4, it's a Euclidean signature I'm going to use. So then I just use the M is R4, or maybe you can just define it as 4 concatenation by 1 point concatenation. So I use gamma matrix as follows: sigma 0 minus sigma mu, where sigma mu is the identity matrix and the power matrix. So this is 2 by 2 matrix. But now we have a 4 by 4 matrix. So you just combine 2 by 2 matrix of diagonal. Okay? And oh, sorry, I think I told you wrong. Sorry, I told you wrong. Sigma mu is minus I. So minus I, minus I, minus I. Sorry. And sigma bar mu is identity I sigma x, I sigma y, I sigma z, and it's bar. And then this will satisfy the following anti-computation relation. So it's a good exercise to do. This is delta 2 times delta mu nu. So this is called Criford algebra. It's called Criford algebra. Okay, it's a Criford algebra from which one can construct. Okay. it's called triple algebra. And Dirac equation can be understood as the follows: I gamma mu partial mu minus m psi equal to 0. So this is for Dirac equation. And that actually is the classical equation of the electron. Classical equation of motion of the electron. And psi can be understood okay, so then this can be this is the Lagrangian equation of the following action. This is the Lagrange equation. Okay. This is the slash partial mu. The partial slash is the gamma mu partial mu. That's the how Feynman used the shorthand notation. And if you use the following I partial mu plus m I partial minus m, okay? So this will give you Klein-Gordon equation. It's a good exercise by using triple algebra. You should do once. So therefore, Dirac equation can be understood as square root of the square root of Klein-Gordon equation. And in particular, this psi can be understood section of so-called spinor bundle. S is a spinor bundle. This can be understood as it's a bit. So you just consider the principal G bundle over M and the principal spin N bundle. Okay, in this case, P is the principal spin 4 bundle. Okay. Oh, okay. So spin 4 is you know spin 4. What's another way to say spin 4? You guys, you do that? SU2 times SU2. You guys do the homework, right? So it can be understood as SU2 plus SU2 principal bundle. And then you just take the so-called associate bundle. B is the row spin 4 to B is called spinor representation. I'm not going to explain representation by using triple algebra. I briefly explained in string theory course what is spinor representation. If you are interested, you can take off from the string theory course. But it's a section. So this Dirac field can be understood as a section of this spinor bundle. And indeed, this can be if so m equal to 0. So massless case. So Dirac equation can be understood as just a psi equal to 0. In this case, massless case, you can just divide it by the following way. Is it 1/2? So where gamma 5 is a chirality operator, gamma 5 can be understood as I already forgot, maybe 1 minus 1, 0, 0. Which is equal to minus gamma 1, gamma 2, gamma 3, and gamma 4. So where gamma is just the matrix I defined here. It's a 4x4 matrix. 4x4 matrix can be decomposed diagonally. It's 2x2 identity matrix, but with minus sign. So therefore, if you combine with one identity matrix, it becomes upper, so plus minus. So 5 plus is indeed 5 plus 0. and phi minus is equal to 0 phi minus. So these are called chiral operators. So in other words, the electron, which is massless, so moves speed of light. But you can just consider chirality in right-hand side or left-hand side. Right-hand side. That's chirality. The spin up or spin down. Okay. So the Dirac field has the spin up and down. So on the how to say the direction momentum, you have the right-hand spinner or left-hand spinner. That's how you define the chirality operator. So the and then So then one can define a Dirac operator. So Dirac operator is this guy. This guy. So this guy is Dirac operator. So indeed, map. So this psi plus and minus can be understood as the section of the positive chirality and negative chirality spinor bundle. So indeed, this is decomposed in B plus B minus as a representation. It's called irreducible representation. It's called, in string theory, I call it 4S, 2S and 2C. Anyway, so in string theory. Anyway, so it's a representation of the right chirality or left chirality. That's how they decompose. Representation decompose. So you know, right? In quantum field, you guys learned this. If you take tensor product of spin one half system, this can be understood the 3 plus 1, right? You learn it, right? 3-dimensional representation and 1-dimensional representation. Do you remember? So if you have plus minus and you have take a tensor product up down spin, one is 3 corresponds to up down plus maybe minus up and minus. Okay, but one is spanned by plus minus minus up down up like this way. So you learn in quantum mechanics, right? So the representation is decomposed by irreducible representation 3 plus 1. Similar thing happen for spinor representation for the massless case. So you decompose to irreducible representation. And then this Dirac operator can be understood, so it's off diagonal. So as you can see from gamma matrix, so Dirac operator partial can be understood as like this way. Maybe I call it diagonal 0, 0. Okay, so that map from so this is section of psi plus, psi minus. Psi plus is mapped to psi minus. Psi minus mapped to psi plus. So therefore, this will give you the section of M of the positive chirality spinor bundle to negative chirality spinor bundle by Dirac operator. So I call it Dirac operator. Okay. Maybe I call it dagger. And indeed, this is indeed in the elliptic type, and the index of this let's call d slash. Dirac operator can be understood as its dimensional kernel of partial difference minus dimensional kernel of it's called zero mode, n plus n minus. I think, yeah, I think I should use this opposite. So n plus and n minus are called zero mode. Number of zero mode. So namely the solution of the Dirac equation. So this solution of Dirac equation is for zero mode. So index of Dirac operator counts number of the right moving or right chirality fermions, fermions zero mode, and left chirality fermions zero mode. And then Atiyah Singer showed that this is indeed equal to a hat of manifold R. Manifold R4, so which is trivial. But it's going to be a bit more interesting when you couple gauge field. When you couple gauge field, everything becomes covariant derivative. D, so d mu is partial mu minus I mu, maybe without mu, maybe plus mu in my lecture. It's covariant derivative. Mu is the gauge field, okay? So then everything d slash, everything d slash, and this one, the Klein-Golden equation of the, I don't remember the Klein-Golden equation including mu. My guess is something like mu plus mu. Is it true? Yeah, I think it's okay. And then here everything becomes d slash mu. This d slash mu is too confusing, sorry. Okay, Dirac and Dirac. Everything d slash. Okay, it's m, and this is d slash, and this is d slash. Then you have to couple to the d slash is a connection. So mu is a connection on some vector bundle. So we just consider some connection of vector bundle, G vector, so this, or principal G bundle, or this is G bundle. And A is a connection. So therefore, you just introduce the term of E, which A hat of M. Okay. So this is Atiyah single index term. So here, I assume M is R4, but you can consider some non-trivial manifold M. And then now, so this index theorem, index of Dirac operator can be computed with Chern character of E, and which a roof genius. And in particular, when M is equal to R4, this is reduces to M Chern of E, M Chern of E, and this is indeed equal to trace F with F. It's just some number times trace F with F. Unfortunately, M is R4. Okay. And this will appear so-called chiral anomaly. So if you open the Pesky and Schroeder in the late chapter, so you will see this kind of diagram. It's triangle diagram, and the J mu 5 up here, and there is a fermions here, and then you have gauge field mu or something. This kind of diagram appears in the QCD and so on. And then this quantity and the difference between right-handed zero mode, Fermat zero mode, and minus left-hand zero mode can be computed by the following quantity over R4 is n plus minus n minus, where the J mu 5 is indeed psi bar gamma mu 5 psi. I think there is I here. Alright, I'm not careful about sign and constant and so on. In this case, there is no I. So it's a Noether current for chiral symmetry. And this can be understood as the 1/8 pi square R4 trace FHF, and if E is non-trivial bundle, then this is no longer 0. So classically, the Dirac equation, Dirac action here is indeed S is given by D4 X D psi bar I D slash psi. So Master's Dirac action is invariant under the psi plus is mapped to e to the I theta psi plus, and the psi minus is mapped to e to the minus I theta psi minus. So it's a chiral transformation. It's called right-handed side is transformed under some complex number, but the left-handed spinner is the transform under conjugate of the U1. That's called chiral transformation. Classically, this action is invariant under this transformation. That's called chiral symmetry. However, it's broken at the quantum level. So it's this J mu 5 is a Noether current of this chiral symmetry. And at classical level, it should preserve. So the Noether theorem will tell us that this is equal to 0. This is equal to 0 by Noether theorem in classical. However, quantum mechanically, so you just receive some quantum correction, so that the this is no longer 0. That's called anomaly, and that can be computed using one-loop diagram, or you can use the index theorem. Index theorem is more elegant. Of course, this originally this other Bell. I think it's a Harvard group. Bell and Jackson. Found that I already found 60, I guess. Around 60 or 70? I don't know the time, to be honest. found that by computing one loop diagram, but this is indeed, it can be computed by indexing. That's the anomaly computed by index theorem. But this is not only the instance for index theorem that appear in quantum field theory. Then nowadays, even condensed matter physics and so on, people use the index theorem or lots of things, eta invariance and so on. This quantum anomaly and computed by index theorem is very important to understand the quantum system of quantum physical system. So any questions so far? 10 minutes left. Let's be ambitious. So let's be ambitious. Let's talk about the supersymmetry quantum mechanics. So we are going back to the first lecture. First lecture, I talked about so-called supersymmetric quantum mechanics in the beginning of lecture, and I will explain how it is related to the index. So let's consider the supersymmetry is a relation between boson and fermions. They call it 1,0 is fermionic, and 0,1 is bosonic state. And the supersymmetry is a relation between them. And for instance, you can define a wave function as following. And you just normalize the delta norm, it's called delta norm. I mean, you just have a proper normalization of the wave function. So they can be understood wave function. And then we introduce the following operator. Okay, so following object where the psi plus and psi minus is just a parametrics defined by this way. So therefore, either psi plus is 1, 0, 0, 0, psi minus is 0, 0, 1, 0. Therefore, once you act Q on these states, Q can be understood as, so this can be understood as Hilbert space is a wave function which decomposes bosonic states, which is lower one, and the fermionic states, then it's the upper one. And the Hilbert space of bosonic states and Hilbert space of fermionic states is mapped to Q and the Q value. That can easily see, so if you act on 0, 1 state, psi plus map to 1, 0 state, times something. Okay? The same, so you have a 1, 0 state, if you map this matrix, it becomes the bosonic states. Okay? So therefore, Q and Q dagger will just map boson and fermion, and then this diagram already look like this one. Okay? Already look like this one. And index L. And you can just check that since sigma plus square is equal to 0 and sigma minus square is also 0, that you can see, right? So that if your computational relation Q is equal to 0, anti-computational Q dagger is equal to 0. That you can easily see. But the question is, what is the Q dagger? Anti-computational relation, and I call it, this is Hamiltonian. Don't get confused with Fourier space. It's upper is Kali one. This is just capital, just H. It's a Hamiltonian. And then you can just compute. Then easily it becomes the x square minus plus w prime square plus 1/2 sigma 3. Okay. Of course, sigma 3 is a power matrix. That's you can easily use. I mean, just plug that one into here, and it just use computation ratio. So therefore, Hamilton. So this is Hamiltonian. It's already look like Hamiltonian, right? So this is p squared plus the potential term, and so therefore W is called superpotential. Of course, I put the h bar equal to 1. I don't like h bar, so I just put the h bar equal to 1. Okay. So therefore, the Q can be understood as a square root. The Q and the Q dagger can be understood as square root of Hamiltonian. So Hamiltonian time translation, okay, with general. And Q is called, as I mentioned, so Q is the map from bosonic state to fermionic states, from fermionic state to bosonic state. So it's called supercharge that relate the boson and fermion. So the supercharge is square root of the Hamiltonian. It's like, as I mentioned, so Dirac equation is square root of Klein-Moulton equation. So there's some fermionic direction in space-time up here. So you can define the time translation, square root of time translation. That's fermionic. And if you have the bosonic eigenstate, if you consider bosonic eigenstate of this Hamiltonian, if EB is non-zero, then you can just apply so sorry, I just skipped one. And you can just check by using this one. By using this one, this is equal to 0 also. Different. And this is equal to, by definition, Q dagger plus Q dagger Q of P. And this is equal to Q. So the bosonic state is first mapped to Q and Q dagger, not opposite way. So therefore, it becomes Q dagger Q. Okay. And then we define F as a superkernel of this bosonic state, just Q acts on B. Okay, then let's compute what is the eigenvalue of this Hamiltonian. Unfortunately, I'm running out of time. Let's compute the eigenvalue and finish. So Hamiltonian acts on Fermat. The Fermat state is Q dagger plus Q dagger Q acts on Q and the Fermat, right? Acts on boson. So that's by definition. So this is by definition. And the QQ square is equal to 0. So therefore, what you get is QQ dagger Q and boson. Okay? And we know QQ dagger B is equal to EBB. Okay? QQ dagger is indeed EBB from here. And this is equal to EB. EB is just number, eigenvalue. Okay? So therefore, superkernel of this bosonic state, it's a Fermat state, have the same eigenvalue of Hamiltonian. So therefore, if you have a Hamiltonian or energy, and you have first excited state, so this is 0. But if you do the excited states, okay, you have always B and there is a Fermat partner. You always have a degeneracy between boson and Fermat. Related by B1 F1, B1 F2, B2 F2. They are related by Q, supercharged Q. Always paired. Okay, it's always paired for Hamilton. But something wrong happens when AB equal to 0. EB is equal to 0. So if it is ground state, there is something wrong, something different will happen. So I already erased, you have a 0 mode n plus one n minus, right? It's a 0 mode of Dirac operator. So we can define the same way, 0 mode of Hamiltonian. 0 mode of Hamiltonian. So 0 mode of Hamiltonian of the boson, so the E0 boson, and then E0 Fermat. This quantity, number of the boson, number of E0F, it's a very schematic, will be computed indexer. That we will see next time. So supersymmetry at the excited state always you have a pair, but the ground state you have non-trivial thing happen. That is computed by indexing. Now let's talk about it next time. And then